Lewis structure, what would you do? This is a condensed form or molecular formula. What would you do if I ask you to draw the Lewis structure for that?
Start by drawing your carbon chain.
Okay, you want to draw the carbon chain out. Now, okay, so remember when we did Lewis structures, what are those two CH3s connected to? Are they connected to carbon or oxygen?
The carbon.
Okay, great.
Sorry.
So you want to draw it out like this. Is that right?
Yeah.
And then what's left? I got a
double bond to ox.
So I'm gonna put a double. You want to put a double bond here and put the lone pairs in here. Is that right? So this is my Lewis form. Is that right?
Yep.
What if I ask you to draw that by showing the electrons, right? How would you put it together? Right, you have a carbon right here with 4 electrons around it. Is that right? That's my central carbon. You have an oxygen here with 6 electrons around it. Is that right?
Yes.
And then for the CH3s, I'm just going to draw them with 1 electron because they already have 3 of the bonds filled in. Right? So what would you do? Now, you can see right here, you got 2 electrons there and 2 there, so you know that was going to be sigma bonds. How do you generate that pi bond? What would you do?
Something with the hydrogen?
To make the double bond between carbon and oxygen?
Oh, never mind.
That's okay. Let me draw it a little bit. So here's my oxygen. I got 1, 2, 3, 4, and I'm gonna put those other 2 down here to kind of try to simplify it. What would you do with this electron right here? That's the question.
Move it to the other side.
I'm gonna move it up. You want to move it up to here, don't you? So now instead of it being here, right, you put it here, and now that explains where your double bond comes from. Is that right?
Yep.
So this is one way to express this Lewis form, right? There's another way that we can express it. And so when we put the electrons in and put the bonds in, we get this structure right here up top. But there's another way to express it, and let me show you. We already been talking about like dipoles and polar covalent bonds and non-polar covalent bonds and things like that. We can also express this Lewis structure a different way, right? Let me show you how. Right, I could draw it this way. Put my double-sided arrow in. I could also draw it that way. What did I do? Let's go through what we see, right? So we see let me make these electrons a little bit more visible too. We see 6 electrons now around oxygen. Right? Now oxygen has a negative charge and then carbon has a positive charge. What changed?
with a double bond.
The pi bond. What does it look like I did to it? Did I move it? Because it didn't disappear, right?
Right.
If you count the electrons, you got 4 electrons here, and over here you got 6 electrons. So those electrons in that pi bond had to shift onto oxygen some kind of way. You following that?
Okay.
All right. The way we show that or illustrate it is by using a curved arrow. Let me erase this. And I'm going to spend some time on these arrows because this is like a really important topic. So I'm going to take an arrow and start it at the pi bond and point it towards oxygen. Right? Here's the part that we all got to get. Like, can y'all still see that?
Yeah.
All right. Where the arrow starts, you see where it starts? Where's that arrow? Where's the base of that arrow pointing?
The pi bond.
It starts at the pi bond. So wherever that arrow starts, that's the source of electrons. Right? And wherever I put the end of that arrow, that means that's where the electrons are coming from. Where the arrow ends, where does it end? Right? It ends on oxygen, doesn't it? Or at least at oxygen. So that's going to be the destination for your electrons. That's very important. Where I start the arrow and stop the arrow, that determines where the electrons are coming from and where they're going to, right? And just for the record, if I have an arrow that's a regular arrow like this with a double head, that means I'm moving 2 electrons. If I have an arrow that looks like this, that means I'm moving 1 electron.
I have a question
Go ahead.
about so the 2 diagrams. So the one to the right of the other one you drew, why is that oxygen not negative but the other one is? Like, where's the so there's 6 around the one to the left, but there's 7 around the one to the right. So I'm trying
That's
to see.
7 around this one. Is that right? Because it's 3 lone pairs and then 1 from the bond.
Mm.
You see the bond between carbon and oxygen right here?
Mm-hmm.
They're sharing those electrons.
Right.
So when I do the formal charge, it's what, valence?
Yeah, so I'm talking about, but for the other one, is that oxygen not negative over? Is that
No.
supposed to be negative or no?
No, it's
Oh.
neutral.
Oh, okay. I
It's got
thought you
6
were
around it total. 2 lone
okay.
pairs and 1 from each bond. So that's 2, 4, 6.
Okay, so I thought okay, so it's not supposed to be negative for the like okay. All right.
Right? So what this structure right here is what we call a resonance hybrid. Right? It's like an average of all of the different forms that are possible for that molecule. Right. So anytime you see a Lewis structure, it's basically it's possible that there are other forms of that molecule, right? And so
Now.
go ahead. Right, but that's not always the case, right? Resonance requires like a really specific set of conditions in order for it to happen. But these 2 structures on the left and on the right are what you call resonance forms. They're called resonance forms. Right, are we okay so far? So in order to draw a resonance form, you need two things. So resonance won't occur unless you have these two things, and they have to be, this is always the case. You need a donor, you need an acceptor, and they have to be adjacent. Right, they have to be adjacent to one another. Let's go back up here to this example. So the donor, which one would you say is the donor in this case?
Carbon.
Okay, in a sense, you're right, but the electrons are even though they're coming from carbon's direction, where are they really coming from?
Oxygen.
No, where are they coming from? From the pi bond, right?
Yes. Yes.
So the electrons are coming from the pi bond, and so in essence, they are coming from carbon, so we can call that our donor, but the actual electrons are coming from the pi bond. Where are they going to?
Oxygen.
Oxygen. So which one is the acceptor?
Oxygen.
Oxygen. Good. So a donor, let me give you a definition real quick. A donor can be a lone pair, or it can be a pi bond, right? An acceptor can be a pi bond or an electronegative atom, or it can be a cation, right? All of those are examples of acceptors. And these two things have to be right next to each other, all right? How can I get back from the structure on the right where everything is charged and unstable? How do I get back to the other structure on the left? What would you do?
Draw
If
arrow
you wanted to
from
put the pi bond back.
draw arrow from oxygen to the line.
Yeah, so pick a pair of electrons on oxygen and do what? Put a curved arrow from there to here. Like that. Is that right? And in doing so, what that indicates is that pair of electrons is now going to be used to make a pi bond between those two atoms. Right? That's why when you draw resonance forms, you draw a double-sided arrow like this, meaning that they're interchangeable.
You said when it like the arrow looks like that, it means two electrons are moving.
Yeah, if it's a double-headed arrow, then you're moving two electrons at a time.
How come you're not just moving the one electron from the oxygen to?
What do you mean? If I only move one electron?
On the right, like when you just drew the pink one,
Mm-hmm.
to like bring it back, how come it doesn't take just moving one electron from the oxygen to bring it back to normal?
That's a good question. But if I only move one electron, I got to use a different arrow. Right? So this arrow is telling me I'm moving two. If I move one electron like that, right, there'll just be a single unpaired electron just sitting there between carbon and oxygen. But the actual charges and all that stuff won't go away. So that's why I'm moving both of them. So that tells me that lone pair is going to become a pi bond between carbon and oxygen.
Okay.
Does that answer your question?
Yes.
All right. So again, in order to do that, you got to have a certain set of criteria, right? You got to have a donor and acceptor adjacent to one another. Your donors can be lone pairs, pi bonds, acceptors, pi bonds, electronegative atoms or cations, and they have to be next door to one another. The best way to do resonance is just to do it. But I need to talk about one other thing, and then we're going to do some examples, right? So one of the things about resonance, the reason why it happens is that it increases stability, right? So resonance gives stability. Let me point that out up here. Do you see how this structure on the right has a negative charge on oxygen and a positive charge on carbon? Even though the whole molecule itself is net neutral, those atoms don't want to be charged, right? And so the electrons on oxygen reform that pi bond to get you back to the structure on the left, right here, right? And we're going to talk more about that, about the stability part in a minute. But the more resonance forms you can draw, the more stable a structure or molecule is going to be.
I have a question.
Go ahead.
Do resonance and entropy, do they kind of relate to each other? Because I thought like with entropy, isn't it when you know, there's disorder, like
Yeah.
so and you said they want to be stable, but wouldn't it normally be like the one that's not as stable? I don't know.
No, not necessarily. You got to think about like stability in terms of overall energy, right?
Mm-hmm.
So if I say that something is low energy,
Mm-hmm.
that I'm also saying that it's more stable. The higher
Okay.
the energy is, the less stable something is,
Okay.
right? But in terms of entropy, when you think about the overall energy of a system, right? You remember
Mm-hmm.
this from Chem, delta G equals delta H minus T delta S, not AS,
Mm-hmm.
right? So this is what you're really concerned about when you're talking about the stability, the
Okay.
delta H, the entropy,
Mm-hmm.
right? The entropic input or the entropic component of that, it really is negligible when you're talking about the overall energy of a molecule.
Okay.
Yeah, that's a
Thank
good
you.
question. You really thinking outside the box.
Thank you.
Yeah, that's a good question. I hope I answered it sufficiently.
Yes, you did.
All right. So let's jump in and do some examples. And I want you to keep in mind these four things. Number one, you need a donor. Number two, you need an acceptor. Number three, they got to be right next door to one another. And number four, the whole reason that I do resonance is to stabilize a charge or to take some electrons and share them over as many atoms as possible, right? That's why I made this statement. The more resonance forms you have, the more stability, because what you're doing is what we call, this is a term that you got to remember, delocalization, right? That's the goal of resonance, delocalization, or to spread either charge or electrons over as many atoms as possible.
Get that one more time.
Right? You're spreading either charge or electrons over as many atoms as possible. That's why it's so important for those atoms to be adjacent to one another, right? The way you share electrons is by overlapping orbitals. If the atoms are not adjacent, then they can't talk to each other. So the orbitals can't overlap and the electrons can't be shared. That's why everything has to be adjacent. All right, so you want to delocalize either the electrons or charge. We're going to see examples of both. And I'm going to point out some patterns to look for too. When you're doing, when you can determine whether or not resonance is possible, there's some patterns that you can look for where you can identify immediately whether or not you can do resonance. I'm not trying to, sorry, it was trying to get me to rate the app at the worst time. Uh-oh. All right, so let's go to this handout, which is in Blackboard. I think it's the second resonance exercise. This is the only one that we're gonna do. I know it's like 3 handouts in there on resonance, but this is the one that we're actually gonna submit. Is that okay?
Yes.
Yes.
All right, so let's look at A. Let's get a good warm up, because this is a good question. And you see right there what the instructions are. I blacked out the instructions from the previous page in whatever book I took this from. It just says supply the arrows to convert between resonance forms. All right, now tell me in A, how could you go from, let's label them, how could you go from A to B? Or could you go from A to B? So first you need to be able to tell me what happened going from A to B. Then you need to tell me if it's possible.
Is there such thing as like a double process or something?
What does that mean, a double process? Like something happening more than once?
Like, could you move the arrow twice? Because I know, like, you can move that double bond and make it a long.
Okay, that's great. You're right, but in this particular case, going from A to B is not possible, right?
Okay.
Look
Right.
at what happened. So I think you're on to something. You agree that the double bond moved here, right?
Mm-hmm.
But how did it get there? How would I show that?
You have to take it
I gotta
outside.
take an arrow and move it like that, don't I?
Yeah.
Is that right?
Mm-hmm.
So that now the double bond is between these two atoms right here. Let me zoom in some. The double bond will be between these two atoms. Right here and right here. Is that right?
Mm-hmm.
But now I have a problem there, don't I? So the pi bond is going to be my donor. Do I have an acceptor to accept that pair of electrons from that pi bond?
No.
In going from A to B?
No.
No.
I don't. So I cannot do resonance here.
Can you tell me why though? Like,
I'm going to go slap this dude on his weed eater. See, he heard me. All right. So what was your question? Tell you why there's not a don't?
yeah, can you tell me why like it can't be an acceptor, right?
Yeah, so let me show you why. So look at this. I want to show you there's two problems with this. All right. Number one, if I did this, I'm gonna show you the structure I would get. I'm gonna draw it in between them. Is that okay? I get this structure
Yeah.
with a plus charge on this carbon. Are you following?
Uh-huh.
But on this structure, now keep in mind, I still got two hydrogens down here. How many bonds does this carbon have to it now?
1, 2, 3, 4. Is it 5?
Is that possible?
No, it's
Not
not
possible.
possible.
Right? Because that carbon is not an acceptor.
Oh, okay.
You following? So I got a donor, but I don't have an acceptor. So if I have one without the other, I can't do resonance. Is that clear? Does that make sense? Remember,
Okay, so when you drew the arrow on the inside,
right?
like, what was that doing?
So I'm trying to get from A to B, right?
Right.
And then B, the double bond is down here.
Uh-huh.
So I'm trying to show how to do that. But in actuality, I can't do it.
It's not possible. Okay.
Right.
Okay.
Because I don't have an acceptor for that pi bond.
Okay.
Make sense?
Yeah, it makes sense now.
I'm gonna put this in red. So that's why I was saying resonance only takes place when you meet those certain criteria, where you have a donor and an acceptor and they're adjacent to one another. Is that okay?
Yeah, that's okay.
All right. So we can't do resonance there. So we can't go from A to B. Let's look at another one. Any other questions about why we can't go from A to B? Now, is there a potential for resonance in A?
Yes.
What would you do? Who was that? Come on. I believe in you. I got faith that you're gonna tell me something good.
You
Come on.
can
What would you do?
you can take it to a lone pair.
Take the pi bond to a lone pair?
Or like, I don't know. I just know you can draw
You
it.
do something. You see something.
you can draw it to the point right there.
All right, I
Like you
want to
can-
show you this right here, right? You see that little part of that structure?
Mhm.
So is there a, when you look at that carbon right there, we know it's partially positive. Is that right?
Mhm.
Because of the dipole that we talked about, like carbon and oxygen, there's a big dipole there. So
Right.
that's an acceptor. Because one of my acceptors is a cation. Is that right? Cations, electronegative atoms, and pi bonds can be acceptors.
Mhm.
And then my pi bond down here can be a donor. So I can do this, right? Now, if I did that, let's walk it down. If I did that, what happens to this carbon right here if I don't do something else?
Doesn't it get a charge?
No, it won't get a charge. You're going to have too many bonds to it, though. Is that right? If I,
Yeah.
Yes.
it's going to have 5 bonds to it if I left it. So now I need to break this bond. I need to break the pi bond. And so now my new resonance form would look like this. So now the oxygen would have, I should have put those electrons in. It would have 3 lone pairs and be negative, and this carbon down here would be positive because I broke the pi bond, right? So I took electrons away from it. But that wasn't the problem, but I'm just trying to, I'm trying to show you that you could do resonance on this, but you couldn't do resonance to go from this to this. All right,
I'm
let's
still
do
trying to
another. Go
understand.
ahead.
I'm still trying to understand like why the carbon wasn't an acceptor. Cause like again, the very first problem we did, and it was the bond between the carbon and the oxygen,
Mm-hmm.
and oxygen got like more negative, and the carbon was more positive.
Yeah.
So how come if you have moved it, like I understand it would be 5 bonds. Like how come you just couldn't write it as like more negative
Why couldn't I just leave it as with 5 bonds?
and put like a minus sign on it?
Oh no. Mm-mm. Mm-mm. I wish I had that, that little dude with the Gucci hat on, shaking his head. I wish I had that right now. You will never, and I'm not saying that to try to be, you'll never draw a carbon with 5 bonds to it ever
Okay.
in life. Not even on another planet. It won't have 5 bonds to it. It can't be hypervalent. You understand what I'm saying?
Okay.
There are other atoms that can go hypervalent, but carbon is not one of them.
Okay.
Yeah. So that's why I wouldn't draw. That would be. So here's the thing about when you do resonance. I'm gonna answer your question a different way. The resonance forms have to be correct Lewis structures, right? And in a
Okay.
proper Lewis structure, a carbon is only gonna have 4 bonds to it, or it'll have 3 bonds and a negative charge, or 3 bonds and a positive, but it'll never have 5 bonds. Does that make sense?
Yes.
Okay, perfect. All right, let's go to another example. Okay, so this is a little bit more clear cut. Let's do B. What would you do? We're gonna label them again. That's A, that's B. Let's put the lone pairs in. All right. What would you do to go from A to B? What changed?
The pi bond.
You got a right here, right? You got a pi bond between carbon and oxygen now, don't you?
Yep.
Is that right? So how do I show the movement of electrons from the oxygen in A to get me to B? How do I show that? I need a curved arrow. Is that right?
Right. Get a curved arrow from the pi bond to the oxygen.
So no, I'm going from A to B. I'm going this way.
From oxygen.
Okay.
So my source of electrons is going to be oxygen, isn't it?
Yeah.
And I'm going to show that curved arrow. Let me fix these long pairs. Why y'all ain't say nothing about how sloppy that was? I'm going to take this pair of electrons and do that. That settles that, right? That puts the pi bond there. Is that right?
Yes.
Now,
Yes.
where you at, T?
Mhm.
Are you there?
Yes.
What do I have to do now? Because I can't leave that. You see on the other structure how that pi bond between carbon and oxygen is gone at the top, right here.
Mm.
See how that's gone?
Yes.
The reason it's gone is because that carbon can't have more than 4 bonds to it. So what's the next thing I need to do? If I put this arrow here in, what do I need to do now?
Fantastic question.
Just think about it. It's very logical, right?
Lone pair.
Look at the oxygen on the right side. It has a sigma bond to carbon and 3 lone pairs. On the left side, it's got 2 lone pairs on the pi bond and a sigma bond to carbon, right? Here, I can just take this pair of electrons and give them the oxygen, right? You see how this arrow forced this arrow. Are you following?
Which arrow are you pointing
This
to?
arrow right here. Once
Okay.
I move that one, that forces the pi bond to break. I gotta move the other one.
Okay.
Right. Let me give you a general example. Right. This is a pattern that you can expect to see. This pattern is what we call an allylic anion. Right. And this at the most basic level is 3 atoms. I'm gonna put carbon here. I'm gonna just put a CH2. It's a very specific pattern. 3 atoms together with the donor and the acceptor adjacent. Which one of those is the donor?
One with the pi bond?
Okay, you under a different set of circumstances, that would be right. But if you have to choose between a lone pair and a pi bond, choose the lone
The
pair
lone
as your
pair.
donor. Is that cool?
Yes.
So this particular system, this allylic anion, has got a really specific flow of electrons that happens every time you see it, right? You're going to take this pair of electrons and move them here. And then the pi bond, you're going to shift that down to carbon number 1, right? And so this is what the resonance form is going to look like. That's negative. And then the double bond is going to be here now.
I see what you're saying, like how it like kind of like moves down.
Mhm. But do you see how, like, so that me pushing this pair of electrons right here forces the breaking of the pi bond? Are you following?
Yes.
Yeah. So this is a pattern. Do you see that pattern right here? Let me erase all this other stuff. Can you see that pattern here? Where you have your negative charge donor here, and you got your pi bond here. It's the same pattern, it's just different atoms. Can you see that? Yes or no?
Yes.
All right. So let me break these terms down too, because somebody's thinking, what the heck is a allylic? Allylic is a term that's used to describe an atom or anything that's adjacent to a double bond. So do you see how the CH2 here is right next door to this double bond right here?
Yes.
Right. So that's why we call it allylic, and it's an anion because it has a negative charge. So that's one pattern that you're going to encounter when you looking for whether or not resonance can happen. That's one of the patterns that you're going to see. Is a very common pattern. It's an allylic anion. And the electron flow is always the same. The anion is the source, and then, or the donor, and then the pi bond next to it is going to be the acceptor. Here's a quick question just to see if you're catching it. What would you do to go from the blue structure back to the red structure?
You will take the lone pair and transfer it again?
Put it right there in between. Is that right?
Yes.
And then what about the pi bond here? Would you do that?
You would break it and put the lone pair on the CH2.
Yep, that's exactly right. Right, so the key to understanding resonance is to be able to find those patterns real quick. Once you find the pattern, then the electrons never change. How you push the electrons never changes. All right, what am I also doing in going from A to B by doing resonance? What am I also doing up there with the charge? See how that oxygen down there has a negative charge? And then that negative charge ends up on a different oxygen in the resonance form. What did I just do to that charge?
Like made it more stable.
You're right. What's the term though?
Neutralize it or something.
No, I didn't neutralize it because it's still negative, but I delocalized it.
Delocalize.
Didn't I?
Yes.
I want you to think about if we were in the gym and I had like 350s, like 50-pound barbells, and I just brought them all to you and put them on your lap. How would you feel?
Weak.
But what if I put those 3 barbells on your lap and then I put somebody next to you who could share them with you? You understand what I'm saying? That would change everything. And so that's what resonance does. It allows those electrons to be shared over multiple atoms. And by default, the charges also get shared. So you're spreading that charge out instead of it just sitting on one atom, like it's sitting here, it's now spread out over 3 atoms. You follow what I'm saying?
Yes.
And that's how you increase, that's how the stability increases, because you're taking that charge and spreading it out over multiple atoms. Let's do another example. Let's do the example down in D. Do you see a pattern in D?
Yes.
Who is that?
Christina.
Where is it?
Well, isn't it between the CH2 and the
Is it here?
yes.
That's the pattern, isn't it? And you see how it fits the allylic anion pattern? You see that double bond and then the oxygen is allylic to it?
Yes.
Once you start to see those patterns, this becomes cake because you never change the way you push the electrons. So now what would you do electron wise? Where would you start? Right? Where's your donor and where's your acceptor?
The donor is the oxygen.
Yeah, why? Because it has lone pairs, right?
Yes.
And then the acceptor is which atom or which group of atoms? It's the pi bond, isn't it?
Yeah.
So I'm gonna do this. If I do this, what is that arrow telling me that's gonna happen? Based on the structure that's on the right of it, what is that arrow telling me?
It's gonna form a pi bond.
Pi bond right there. Is that right? And then what is this? What happens to the pi bond down here?
It turns in a lone pair on the CH2.
On carbon. That's exactly right. And I have to show that, right? Otherwise, this carbon is going to be real pissed off if it's got 5 bonds to it. And that's never happened in the history of chemistry. Right? Yes or no? So these two are interchangeable. How would you go from, let's label them, A, B. How would you go from B back to A? What would you do?
Just flip the arrows.
Change. So now the anion right here is your donor, right?
Mm-hmm.
Lone pair suck today. And then oxygen becomes the acceptor. Do you see how you interchange those structures?
Mm-hmm.
right? So that's an example. Both of those B and D are both examples of allylic anions. Let's look at F. F is a little bit different. What do you, let me put the lone pairs in. What happens in F? Where's your donor? Where's your acceptor? On this side, let me call it. That's A. That'll be A, and that'll be B. Where's the donor in F?
Would the donor
Go ahead.
plus,
Go ahead.
would the donor be like the plus sign or something?
I'm glad you said that. By donor, what I mean is something that can donate electrons.
Mm-hmm.
So if the carbon is positive, that means it doesn't have electrons to give away. That's how you get plus charges, right? By taking electrons away from atoms.
Okay.
So any atom that's positive is not going to be able to donate electrons. It's looking for electrons, right? So the oxygen has 2 lone pairs on it, whereas the carbon has a plus charge. So the donor is always going to be the atom that's more electron rich. And then that makes this the acceptor. Is that okay?
Mm-hmm.
So when you push electrons, you always push from donor to acceptor, never the other way around. So I'm going to take this and push it here. Is that right? That gives me this structure on the right, doesn't it? Yeah, it gives me that structure, right? Now oxygen has a plus charge. Can somebody tell me why? By
Because it has
calculating
5 bonds.
5.
I mean, 5 electrons.
Yes. 2 from the lone pair, 2 from the pi bond and the sigma bond, or 1 from the pi, 1 from sigma, and then 1 from hydrogen. So the formal charge is +1. Thank you for saying that. All right. Can somebody tell me why the carbon over here is positive?
Because it only has 3.
It's only got 3 bonds. And the formal charge on a carbon with 3 bonds is +1, unless it has a pair of electrons. Then it becomes -1. So this is another unit, right? This is another pattern. You'll see this again. You see how you have 2 atoms. I'm gonna write it like this. Sorry about that. You got 2 atoms together like that, and then one of them is positive, and then one of them has electrons. So you have your donor and acceptor are directly connected. That's a pattern that you're going to see as well. I'm gonna call it. What do I want to call it? It's technically called a Ritter Ion, but you can see here where you have. I'm gonna make that negative. So you have your donor and your acceptor, and they are right next door to one another. So this is the acceptor, and then this is the donor. That's one pattern. That's a pattern that you're going to see a lot of. So the allylic anion is a pattern. The Ritter ion is a pattern, and then we haven't seen yet the allylic cation and the allylic radical, but those are patterns too. Any questions about what we just did? All right, let me show you real quick. There's a handout in Blackboard that has the patterns on it, and I'm gonna pull it up. Come on, this computer, I promise you, it's a dinosaur. Come on, man. This hard drive is terrible. let me share this my screen right quick. So right here in where are my modules, man? Oh, no, that's the wrong class. My bad. So let me pull this handout up with the different patterns in it, and then we can look over. I'm gonna talk about that for a second, then we will be done. We only got 4 minutes left. So, are there any questions about what we've done so far? About anything?
So we need to turn in this worksheet too, just that section that we did today.
We'll turn once we're not done with it, so we're gonna keep working through it.
Okay.
And then wherever we stop, that's what you'll turn in.
Okay.
So right now we're in module 1A, first module 1A, and then the handout is in the same folder. It's in the assignments folder. And the one that we're doing now is this handout. Right, we're going to talk about those functional groups probably Friday. I'll send that video to you later on in the week, but I want to get resonance out in the open first before we do functional groups. So this is the handout, but then this handout where it says problem set 1, that first page of that handout, I recommend that you either download it or print it because it has the patterns on it that you have to look for.
Wait, where are these assignments at?
It's in the module right here, first module 1A. If you scroll down to the assignments folder, it's in there. All right, so let me do, I'll just open it up or save it.